So welcome. So in this talk, I would like to discuss how the local completeness logic can be interpreted on a Kleene Algebra with tests. So, but first, I would like to discuss what do we mean with program logic. So, program logic is really an application of mathematical logic to program semantics. So we can derive several kinds of facts about programs. For example, input-output, the relationships between the input and the output, memory usage, and execution time, and so on. In this talk, we'll be interested in input-output behavior. Several program logics have been proposed to tackle these kind of facts. We have, of course, the fundamental logic from Hoare, but very recently also the Hoare logic. And in this paper, we focused on the local completeness logic, which is kind of a combination in a certain sense of the two performed two. So to give you a brief introduction, very quickly, I described in this figure a program execution as a transition system in which states are represented as dots. So we can start from a precondition P on the left, and from there the program is really modeled as a transition system. So we transition into multiple states, and in the end we reach some output states here. The strongest postcondition is defined by the collecting all the output states. Of course, the program may loop like in the green states, or can be also stuck in some orange state. So that may be useful to represent, for example, an exception. And I will also remark that it is also possible to have non-deterministic behavior. So back to the local completeness logic. So we can derive triples of that form. So P, C, Q. And the semantic of the local completeness logic is that the postcondition Q is an under-approximation of the strongest postcondition. And this logic is also parameterized by an abstract domain. And in particular, we can derive an abstraction function. I will be more formal in the next slide. And the abstraction of the postcondition is instead an over-approximation of the strongest post. So the strongest post is like bounded between the A of Q and Q. So in this sense, it's similar to Hoare logic. To be more precise, A is defined as like this, using the gamma and the alpha function of the abstract domain, parameterizing the logic. So it given some condition, it returns the most precise way to the most precise representation of this condition into the abstract domain. We can now go on to continue with the semantic of LCL triples. So we have three properties. The first one that we have already seen is that the post condition is an under-approximation of the strongest post. Here I denoted it with the concrete semantic like this. Then we have that the post condition and the concrete semantic and the strongest post have the same representation in the abstract domain. And finally, the abstract interpretation of the program C is locally complete on the precondition. So up to now, we have seen how we can formalize this local completeness logic using a sector-theoretic framework. So using representing conditions as sets and the program semantic as a transition system. But we can also use an algebraic way of formalizing program semantic. In particular, I would like to discuss a very suitable algebra for this, which is the Kleene Algebra with tests. So typically referred as KAT. So a KAT is a set of programs. So a set of elements more in general that we interpret as programs. We have three main operations on a KAT that are the plus, which is interpreted as the non-deterministic choice between two programs, the product, which is the sequential composition, and the star, which is the linear iteration of a program. There is also a subset of a KAT, which is called the set of tests. Tests have the purpose of representing conditions into the KAT, and as tests are a subset of a K, they are also programs. And in particular, they are programs representing Boolean filtering corresponding to the proposition. There is also a partial ordering defined on this KAT, which corresponds to in the set rating framework to the inclusion. And we can see that the set theoretic operations can be easily translated into the algebraic framework. But why would we like to use this KAT framework instead of the set theoretic one? So first of all, a KAT is a completely abstract algebra, so we don't have a specific model. And in this way, it can be used with several different models, provided that they satisfy the axioms of the KAT. And also it's very useful because it allows to reason in an equational way, so in equational form, to test, for example, inequality or also equality of programs and also conditions proposition in the algebra itself. Unfortunately, the KAT is not able to represent fully Horn triples and so also neither LCL triples. This is a result by those authors. For this reason, we can't represent LCL in a plain KAT. We need to have a richer structure. In this paper, we consider two variants of KAT that are the Modal KAT and the KAT with top. Starting from Modal KAT, so in a Modal KAT, we have for any program represented as a KAT element, and for every precondition represented by a test, we assume that there exists a particular test in the set of tests, of course, which represents the strongest postcondition. We represent such test with this operator, which is called the backward diamond operator. And now we are back to the previous problem. So how can we encode those two free formulas, which are the semantic of the LCL triples in the set theoretic framework, using KAT formulas? So the first one is easy because it only represents the inclusion. So we say that the postcondition is an under-approximation of the semantic, and we can do that using the KAT because we have the strongest postcondition, which is represented as the backward diamond. The precondition and the postcondition are represented with tests. We have instead some problems with the other two formulas because we need also to have the abstraction function, but we don't know what an abstract domain is in the KAT framework, and so we need to do that. So in the set theoretic framework, an abstract domain is typically defined as a Galois connection between the set of the power set of all stores and a domain A. And here, the power set of S is represented by the set of tests. And so we can easily define an abstract domain in this context as a Galois connection like this. We can also define an abstract semantic by structural induction on the language. And it turns out that even in this context, provided that there is this CTC condition, and it's a very technical condition, but provided this condition, we can show that the abstract semantic is monotonic and sound. We can now proceed to adapt the proof system of the local completeness logic to this KAT framework. I want to give you two examples of two rules. So here we can see that we can really perform a syntactical substitution to obtain the corresponding algebraic version of the rules. So the conditions such as P or Q1 are here represented as tests such as P and Q1 again. The union here is converted into a plus, which for tests is like also the union of tests. And then the inclusion is replaced by this subset, the less or equal operator. We can now proceed with the formalization of the free conditions using this KAT language, and we obtain this result here. Now we can proceed with verifying if the result in logic is logically sound and complete, and it turns out that this is true. At least for the logical completeness, we need also to have some additional hypotheses on the atoms of our language, but this is also the same for the set theoretic formulation, so we are not adding any other hypothesis here. The second formulation that we considered is the formulation of using not a Modal KAT, but with a KAT with top. So a kat with top is simply a plain kat, a normal kat, in which we add a new element called the top element. And this top element represents, is bigger than any other element in the kat. So it represents a particular program which resets the execution. And it was shown that under this, by adding this new element, we can encode OR logic we can encode OR logic, and that was not possible with the plain kat instead. Here I want to give you an example of why this top element can be used to represent a program which resets the execution. So let us consider the relational model of KAT, so a model like the saturated model. So here we consider a precondition which contains only one state, this one in red. And we can see that after executing the top element, which in the relational model corresponds to the full relation, because it's considering the ordering by inclusion is the biggest element, you obtain this as a postcondition, all the dots here, so the full postcondition. And if you consider another precondition, such as x equal to 0 or x equal to 1, we obtain again the full postcondition. So no matter the input, we obtain always the same output. So that's why we consider this is interpreted typically as an element which resets the execution. We can now go back to our problem. So we need again to encode those three formulas into the KAT. So again, the first one is easy. So this encoding is again from the other papers, the one in which they presented TopKAT and how that can encode OR logic. But the other two formulas are not very clear because again, we don't have a definition of abstract domain in this context. So as for the Modal KAT, we need to have a way to represent the set of propositions. Unfortunately, here we can't use a set of tests because here we don't know whether because we don't have the strongest postcondition operator which returns a test. So instead, the intuition is like to use this encoding here of this top PT element. So this is in a certain way represents a proxy of the strongest postcondition. And we can thus represent the propositions using this kind of proxies elements. Again, we have another problem, which is in which domain do those proxies live? And in general, they're not the set of all the top tests. And by top test, I mean the set of all tests in which we prefix the test with the top. And we have a counterexample for this in the paper. So we take a very straightforward approach and we prefix the entire algebra with a top element. And so we obtain this very big set. This is, of course, a very coarse approach, but an initial approach, I would say. And it turns out that this works. And under this star continuity hypothesis, which plays a very similar role to the CTC hypothesis, we can define an abstract semantic, which is sound and monotonic. We can proceed with the definition, with the construction of the validity of the validity of the LCL triples, even in this context. And here we have the formulas. And it turns out that the resulting proof system is logically sound and complete, again. So in this paper, we have done something more. We have also considered a reduction of this LCL logic. So LCL logic using the KAT formulation to under-approximation logic, where the under-approximation logic, we mean the OR logic, in which the triples have only a single postcondition. And we have shown that, again, using a particular abstract domain, which is the trivial abstract domain, we can obtain this under-approximation. That was also done in the original LCL paper, but we have shown also that this can be done also in this algebraic formulation of the logic. We have also generalized the logic to include also incorrectness triples, so triples in which there is both an OK and an R postcondition. And finally, we have also provided provided an example of a model of this algebra, which is not related to program semantics, just to show that this whole idea of using a KAT is also useful in different domains. So in conclusion, in this paper, we have shown how to encode the local completeness logic using two variants of KAT that are the Modal KAT and the TopKAT. This is a generalization of the original presentation of the local completeness logic, because they used a set theoretic framework, which is a particular instance of a KAT, so the relational model of KAT in particular. There are two open questions that we have. To formulate the abstract interpretation, we need to have the intensional properties of programs, because you can easily have two different programs that are semantically the same, but that may have a different abstract interpretation. And so to perform the abstract interpretation, you need to know how the program were originally written. So in a certain sense, you need to have the source code of the programs. So unfortunately, we have that in a KAT, those properties are not stored in general. For example, in the relational model, those properties are not preserved. And so we had to use an inductive language to perform the abstract interpretation. But this is not very natural in the context of KAT. And a follow-up for this work will be to consider some conditions and to more formalize what do we mean with intensional properties, and to study a possible variant of KAT in which those properties are preserved. A second question, we would like to study a bit more the set of top tests that are needed to perform the abstraction in the context of the TopKAT formulation. So in particular, we would like to see under which condition the proxy TopPT corresponds to some top Q, where Q is a test. So in this way, we could add some, so we could abstract only a smaller set of elements and not the entire top algebra. So with this, I would like to thank you for your attention, and I would like to answer your questions.
Thank the speaker. We are way in advance, so we have time for questions.
Hello. I was a bit confused about the tests. You said that you have a test for every strongest post condition. Is that usual in KAT? Because in KAT you have I would say, a limited set of tests, right? And you don't know what the program actually does.
So can
you
by test, yeah.
Yeah, but for the programs, you don't have an interpretation of the programs, right? So I'm confused why you have a test for every possible strongest post condition, even you don't know what the program actually does.
That's an assumption of Modal KAT, so that you can have all for every program and for every precondition represented as a test, you have also another test in the set of tests, of course, which represents the strongest post.
Yeah. Even though the program is completely uninterpreted, you have all the tests in there. Okay. All right.
Yes.
Thanks.
Other questions? Roberto.
Hello, thanks for the nice talk. Incorrectness logic had then been extended to incorrectness separation logic for pointer analysis. Do you think the algebraic framework can be extended as well?
Yeah, that's a good question. I'm not really familiar with a variant of KAT, which can also deal with the separation logic with memory. So I'm not really sure about it, to be honest.
Yep.
I wonder, have you considered extending this result to concurrent Kleene algebra and having a version of LCL maybe that support.
Sorry, with concrete Kleene algebra?
CKA's concurrent Kleene algebra.
Concurrent, okay.
And whether that result would extend to the concurrent setting.
Yes, so do you mean a version of concurrent of the local completeness logic, which is also deals with concurrent programs? Do you mean?
I guess if you had a version of LCL that could cover that,
Oh.
maybe you could have a correspondence with concurrent Kleene algebra.
Yeah, probably, yes. Yeah.
Is there something that you're working on?
No, right now, no. But
or anyone else?
I see. Yeah, but first, I think you will need to also have a saturated version of this local completeness logic with the concurrent version. Yeah, and then you can certainly proceed with the algebraic version of it. Yeah, but I don't think that why that wouldn't work, because we already have a version of KAT for that. Yeah.
If you have more time for more questions, in case. Yeah.
Since we have time, the top program, the top element in your Kleene algebra, is there any operational interpretation? You were saying you are resetting, but in terms of strongest post conditions, how can I think about the top program?
Oh, it returns basically the full post condition. So a post with true, basically.
True.
True.
Always true for any
input.
Precondition.
Yeah, the idea is that you completely forget the memory, basically. So you reset your memory when you execute that thing. So the idea of that encoding.
No.
Sorry? I don't know. Okay, thank you. So the idea of this encoding here is that if you have so you want to encode again the Q include smaller or equal than the strongest post condition. That would be the concrete version of it, so the saturated version. And you can do so. You don't have the strongest post condition here because you're in this. You are not in the Modal KAT. You're in the TopKAT. And to do so, you can use this top element, because like if you didn't add the top, you will have PT, which is which is a program in which you have firstly you filter for these states satisfying the precondition, and then you execute the program. And that is, again, a new program in which, starting from the precondition, you obtain the output. And then, on the other side, you have the post-condition Q, which is, again, a test, but they differ on the precondition. Okay, so while on one side, you have only a program which filters the states satisfying the post-condition, on the other side, you have a program which takes the input, does some computation, and you get the output. And so that way, without the top, that encoding wouldn't work. But instead, if you add the top, you are completely forgetting the input. And so you can make that encoding working. So that's the idea behind this encoding, and why you need an element which performs this kind of memory reset operation.
Follow-up question. Are you familiar with assume statements? Assume statements. Assume blah, blah, blah.
Yeah.
So can I express top in terms of assume false or assume true?
Top can be no, because assume is like assume in this case is a test, basically. Tests are assume. And because you mean like if the assume is satisfied, it acts like a NOP. Otherwise, it is an infinite loop, basically, right? Something like that. You mean is?
I don't know.
Yeah, I mean, if you start the program, you're assume with some state satisfying the assume, you're not doing anything.
Yeah.
If you're starting with some states not satisfying it, you end up in an infinite loop, basically, or you throw an exception. No. Yeah. And anyway, that is not what top does, because top is not a test in general. And because it also adds like new states. So we assume you only filter states. You don't
I
add-
think you're thinking about assert, right? As a filter. But assume says, I assume I'm established, or I'm in this test now. Yeah, you make it.
okay. If you think in that way, yeah, probably makes sense.
Maybe.
Yeah,
Oh.
maybe, yeah, okay. Assume true probably would be correct.
Okay. Cool. Thanks.
Other questions? I ask one or maybe two, it depends. We have to be in time for your speech. So, I mean, if anybody wants to come in at your speech, it's better to be in time. So, you mentioned that abstract interpretation reveals and program analysis reveals intentional properties of code. So, there can be two programs that are equivalent semantically, extensionally, but they expose different behavior when they are analyzed. And this, of course, cannot be catched, cannot be obtained in the KAT. Do you have an idea on how to recover this information within the KAT? Within this way of presenting?
It's not easy because I think you need to define precisely what do you mean by intentional property, and probably there isn't only a single way to define it. And so you firstly think you need to formalize this idea, and then you need to encode this within some actions that would be needed in a KAT. So that I think would be the approach, but it's not straightforward. I wouldn't see an easy solution for that.
Okay. So maybe if you come out with a definition of this intentionality, you have somehow a reference on where the analysis will fail in case of some code transformation. Okay.
Yeah, thanks.
Okay, we are set. Thank you. Let's thank the speaker again.